Okay, let's test our knowledge of conservation laws and let's examine a few particle reactions and see what may be going okay and what may not be going okay, or what is conserved or not. So first reaction up to bat, a proton and an antiproton combine, they annihilate and make three pions, a pi plus, a pi minus, and a pi plus. Now let's take a look at this. What's happening here? We have a proton which has electric charge plus 1 unit of E, right? So we have plus E here. We have minus of that for an antiproton, so it's negative E. Then we have plus E for the pi plus, minus E for the pi minus, plus E for the pi plus again. So on the left side, we have net charge 0, right? Q on the left side was 0. And Q on the right side is plus E minus E plus E is plus 1. So Q on the right side equals plus E. And so those don't equal. Electric charge is not conserved, right? That should be pretty obvious. So let's put an X in front of that reaction. That one doesn't go. All right, another reaction. Let's talk about a delta plus plus baryon decaying to a proton N pi plus. All right, now, and I'm just telling you the delta is a baryon and has double charge. So there's two plus signs there and going to a proton plus pi plus. So here it looks like the charge is okay, right? So charge is okay here. We got two pluses on the left side and we have a proton which is positively charged, pi plus which is positively charged. Everything's okay there. Let's see, what about energy and momentum, or in particular energy in the form of the mass energy? Let's look at the mass. So we don't have it listed here, but you could look it up that the mass of the delta is 1232 MeV. The mass of the proton is 938 MeV. And the mass of the pi plus is 140 MeV. Now 938, which is about 940 plus 140 would be 1080, and that is less than 1232, right? So that is less than the proton plus pion mass. So that's okay too. So mass is okay. And what about strangeness? Are there any strange particles here? Well, the delta plus plus is not a strange particle. The proton's not strange, and nor is the pion. So strangeness is okay also. Nothing is strange here. Strangeness. Okay. So actually everything's okay there. So that reaction goes. All right. All right, let's talk about third reaction. How about the decay of a pi minus to a tau minus and a photon? Electric charge looks good, right? There's a negatively charged pion and a negatively charged tau lepton, and the photon's neutral. Let's look at the masses. All right, we talked about the mass of the pion was 140. We have to look up what's the mass of the tau lepton. The mass of the tau lepton turns out to be 1,777 MeV. Now, can a 140 MeV object decay to a 1,777 MeV object? No. So that's less than what it's decaying to. The photon, of course, is massless. So this one does not go. What about a kaon decay to pi plus, pi minus? Well, what's the mass of the kaon in this case? Well, the mass of the kaon is 497 MeV. The pions we know are 140, and so indeed, this is less than 140 plus 140, or which would be 280. So no trouble there. That's good. There's enough energy for that decay to go. How about electric charge? Well, I have a neutral kaon, right? A plus and a minus pion. Charge is okay also. What about strangeness? The left side, the K0 is definitely one of those strange particles, right? And the strangeness there would be +1 for the left side. But on the other side, the pions are not strange. They're so 0 plus 0, and that doesn't equal 1. Right? So it does violate strangeness. So the only force that this reaction can go by is the weak force. But in fact, this reaction does go. So it can't happen by the electromagnetic or strong nuclear force, but it can go by the weak force. So we'll give it that it can go with the caveat that only the weak force because strangeness is violated. Fifth example, proton plus an electron neutrino turn into an anti-electron E plus, a lambda, and a K0. And I'm sorry, my work is a little bit overlapping there. So the neutral K0, I should also add that the lambda is also neutral. So we're going to stick in a little 0 here that the lambda is neutral as well. Okay, so electric charge looks like it's not a problem here, right? We have a charged proton plus E, neutral neutrino, and we have a charged electron plus E. Everything's good, the rest are neutral. So electric charge is okay. We're making some other particles, the lambda 0 and the K0, and this is a different thing. This is not a decay, this is a reaction, right? We have a proton and a neutrino colliding. So we're going to assume enough energy. So we'll assume enough energy for this reaction to go. But let's talk about the strangeness here. We do have some strange particles on the right side and none on the left side. So we can talk about strangeness. On the left side, we have a proton and neutrino, and they're not strange particles, so it's 0. On the right side, we have the electron, that's not strange. The lambda 0 has strangeness, whoops, I should, of -1, so it's -1. And the K0, as we noted before, has strangeness +1. And does 0 equal 0 minus 1 plus 1? It does. So that goes. So everything is fine there on strangeness. But what about electron-lepton number? For the neutrino, the lepton number is equal to 1. But for the anti-electron, the electron number equals -1. And the other particles are not electron types, so they don't have electron number. So the lepton number, the electron type lepton number is violated. So that's what didn't go, and so we put an X there. Finally, what about a proton and pion collision making a lambda and sigma 0 bar, an anti-sigma 0? Again, we're going to assume enough energy so that you can make the right side. So I'm not going to look up the masses there. What about electric charge? We have proton, which is positively charged, and pion, which is negatively charged, so it's neutral on the left side. But I have two neutral particles. Again, the lambda is neutral. Okay, we're assuming enough energy, charge is conserved. What about baryon number? All right, baryon number is +1 on the left side, so we're going to talk baryon number. B equals +1 on the left side. What is it on the right side? On the right side, we have, for the lambda 0, it's a particle, so it's +1. Now, sigma 0 bar is an anti-baryon, so it's -1, which equals 0. That doesn't work, right? 1 does not equal 0. So baryon number is violated in this case. All right. Okay, so those are just some examples of working through a few reactions to see which conservation laws apply and which do not. And this last one did not, it's not allowed to go because it violates baryon number. Okay, that ends this lecture, going over some examples of how to test the conservation laws for some reactions and decays.